Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Chamberlain.
And this is Chris Jackson. We're going to talk about system reliability modeling, or at least a specific instance where I think one of our listeners is struggling to use a reliability block diagram to characterize some of the intricacies associated with his or her system in his or her work. Is that right?
Yep, that's right. The question had two parts to it. One was, how do I model? I'm doing a block diagram and for our system, and we have a pressure vessel that has a relief valve on it. How do I model the relief valve on that in this system? And the second question, which then expands this into something I thought we could talk about, because I know you like talking about system models and stuff, is they had a valve that positioned in three different orientations, and it sounded like it would redirect whatever was in the pipes to three different processes. And I thought, how do you do that in a block diagram? Model this valve, and I think there is a way, yet it's a bit more complicated than series and parallels and stuff. But it made me say, I need to talk to Chris. But my very first response, which I think I was mimicking you or channeling you in my response, is, well, what are you trying to achieve? Do you need to model at the pressure vessel and valve level, or is that for what purpose? Is this for maintenance? Is this for optimization? Is this for this or that? What are you trying to do? What's the point? And once you get into enough detail and you start having models that have all this conditional elements on it, depending on what state they are in, if they're in a repair state or a cleaning state or in production state, maybe you have different kinds of materials going through this pressure vessel at different stages, and they behave differently, and their chance of failure is dramatically different, and chance of that pressure valve working or not working change a lot. Well, then your block diagram can get really complicated. You might want to look at some other models.
Right.
But it starts with, what are you trying to do? Like we always talk about.
I think when it comes to block diagrams and fault trees, they're essentially logic diagrams. We often think it's, okay, you see a parallel system in a block diagram, therefore the equation is this. And the block diagram doesn't say that. It doesn't say it's a parallel system. It doesn't say that you can use that equation. It just says the system doesn't work if these two components fail. Now, you can use an equation where you assume that those failures are independent to come up with a number. You can use another equation where you can assume that there is, 10% common cause failure probability between the two of them, and you'll get a different number. You could even argue that parallel or seemingly parallel system in as it looks on a reliability block diagram, it still applies to switching systems where either of the main or backup components will, if they both fail, your system fails. And I think that a lot of people look at things like fault trees and reliability block diagrams and say, okay, that's parallel, therefore the equation is this. And RBDs and fault trees aren't telling you which equation to use. That's up to you. All they're saying is your system will fail and these two components fail. If you're going to use that equation to calculate that probability, that's on you. But it's not.
But it includes a handful of assumptions that make it simple. If they're independent and both capable, and the chance of failure doesn't change because the other one's not working. It doesn't. All of those kinds of things simplify it, so we get the textbook simple equation, and off we go. But that's the hazard, right? Is, well, what's your system really doing? Because I've heard this some places. Gravity really doesn't care. It's just going to do what it's going to do. Reality is, you can't wish it away. It's going to do what it's going to do.
Yeah, and as long as we understand what RBDs and fault trees are there for, there's logic diagrams. It's up to you to use this thing we tentatively call critical thinking to work out what equation you should use. And some people will say, "Oh, what standard tells me which one I should use?" Go, well, let's go back to critical
Yeah.
thinking.
Yeah. Which is going to a standard is a sign that there's not much thinking going on.
Right. And so if you make an assumption that everything fails independently, which is actually that's what you want, independent failure for redundant components promotes system reliability. That is, dependent failure is the enemy of reliability when it comes to redundancy.
Isn't that even have its own special term like cascade of failures
Or common cause failure.
or well, common cause, but I'm thinking of where one component fails and it causes an overheat that causes that to fail, and then that shorts out this and that causes the
Oh, yeah.
next one to fail. It's a cascading event series of
Right.
events.
Those cascading failures or cascading events are a subset of common cause failure. So, for example, if you again, if you have a pump next to another pump, and the first pump fails catastrophically with, you know,
Shards of iron flying around.
flying everywhere and takes at the pump next to it, that's an example of a cascading failure or cascading events, which is common cause failure.
Mm-hmm.
Another more subtle example of common cause failure is when you have both those pumps installed by the same installation team. And if that installation team is either inexperienced or is using the wrong processes, then both pumps will be incorrectly installed. And so they'll both have a fault from a common cause, and they'll both tend to fail early as a result. Even though it's not cascading, that's still an example of common cause failure where
Mm-hmm.
unfortunately the redundant pump isn't as redundant as you'd like it to be because they both share the same issue.
Right.
But
Well, that's where I know even myself is hesitated to go into the modeling going, well, how do I deal with this common cause stuff? How do I deal with this, one failure is not independent from or the failure rates are not independent. The I think it's possible, but that's where the basic books say, no, no, no. You just assume they're independent, assume they're this, and don't worry about common cause. They don't even mention it in most of the textbooks. Here's parallel, here's series, here's,
right.
the more complex ones. And that's all you need to know. You're good.
Well, I think the other thing though is that, what's the decision you're trying to
Yeah.
win?
If it's a real simple, basic idea of where do we need to focus next on these big chunks of our logic diagram, then it can be pretty straightforward and simple. If it's getting into the nuances and getting into those dependencies and the common cause elements of it, well, then you need a different set of formulas.
Well, even if you need different sets of formulas, let's just say you're trying to see if your system meets or exceeds some sort of reliability requirement. Let's just say that.
Okay.
If I model a complex system with redundancies, okay, here's my model. All right, I'm going to assume there's zero common cause failure. I'm going to assume all failures are independent, which is rarely the case and essentially overstates reliability. And if the answer I get is essentially an order of magnitude better than the requirement, I'm going, we're done. Yes, we're overstating reliability to an extent because I didn't take into consideration common cause failure. However, we are so far beyond the requirement, we are cool. Move on.
Yep.
And so that's a scenario where, assuming independence might be okay just because the sort of judgment you can use to accommodate any discrepancy through common cause failure is just overwhelmed by the fact that you are an order of magnitude better than what your requirement says you need to be.
So is that,
sorry?
So I was going to say, is that same kind of logic apply? And I've used this example. I know you've heard it before, is that you have a series system, say it's a workstation or a computer, and you get an estimate for each of those blocks for the motherboard and the hard drive and power supply and so on. And then the program manager looks at the one that's the lowest reliability of the whole group and says, all right, Sarah, you need to go improve the reliability of your part. We'll put our focus and resources on the weakest link, and therefore our system will be better. But that's a totally simple, can be done on a whiteboard in 5 seconds and come up with engineering guesses or historical data or whatever for the estimates. And we're not assuming any dependence or any common cause or anything else, but when does that trigger that you need to consider common cause? What's the threshold for that kind of decision or even in the one you're talking about is when do you have to do something better?
Well, firstly, for a series system, common cause failure really doesn't matter from a system reliability perspective.
Because it's whatever fails first is done.
Right. So if the thing that fails first takes out every other component in the system, I mean, that might be bad in terms of the consequence and the amount of damage it causes and how much it costs to rectify it, et cetera, et cetera,
Yeah.
et cetera. But it won't change series system reliability characteristics. Common cause failure only becomes a thing when you have redundancy. And the other thing too is that common cause failure tends to occur between components which are similar. And as a rule, you're less likely to have similar components in series systems because each component is providing a separate, unique, indispensable function. There's no backups, so to speak.
Yeah.
But it does come into judgment to an extent. I mean, because if you are close to the requirement, sorry, if you model a complex system with redundancy, assuming independence, and it's only just meets the requirement, that's when you would be philosophically interested in, or should be interested in getting on top of common cause failure, because that might then push you below the threshold. But then you can really look at it in a smart way and say, okay, if I do have common cause failure, it's going to be occurring at redundant subsystems. Let's focus on that.
Yeah. Okay. No, it's not like a hard and fast rule. It's a judgment call. Is do we add the next layer of complexity to do this? And it goes back to that very first comment is that it depends on what you're trying to do.
Right. That emergency relief valve, though, that's an interesting one because, I mean, a system could be happily working, so to speak, with a busted emergency relief valve.
Mm-hmm.
So you just need to, it's a little bit more depth, that question. Would you not agree that you have to define what failure is? So, for example, if the system appears to be working brilliantly, but the emergency relief valve has failed, then your system is in a failed state, even though it appears to be working magnificently. Right. It's a different failure mode. It might mean
it's a safety hazard. Is
right.
The chance of a catastrophic failure goes to a different level. So it's
right. And so you might want to take the time to actually have multiple, reliability block diagrams based on different failure definitions. So you'll have a reliability block diagram for safety critical failures. You might have a reliability block diagram for operational failures where one describes the likelihood of you being able to do your job. The other one describes the likelihood of you dying, which are not necessarily the same.
That's right. So, well, I'm imagining my boss telling me years and years ago, I was doing an experiment and I showed him the results and goes, well, that's not right. And I said, what do you mean it's not right? Here's the data. Here's the calculations, all this stuff. This is all correct. And he goes, oh, I don't disagree with any of that, but it's not the answer I wanted. So go try it a different way. Keep testing until you get my answer. Like I asked him, why don't you just tell me the answer? Then I don't have to go back to the lab.
And technically, I mean, I was about to say technically he's right. That's not my intent, but technically because the things you're examining is a random process. If you run enough tests, you'll get the answer he wants.
Yep. Although
it might take a million.
Yeah, no, I later showed that it was like not possible. He was looking for like a negative time to like a location parameter that was a negative value or something like that. But I think that was his way of making me dive deeper into the assumptions being made and all other good stuff. He was clever that way.
Oh, so it was a good thing. Is that right?
Yeah, no, I learned a ton, and there's no doubt about it. But he had a unique educational style.
That's cool.
Yeah. Now, one of the other things, I mean, at some point, I know that block diagram is not the way to go. I need to account for more shades of gray. It's not either working or not working. It's partially running, or it's in a maintenance state, or it's in we're doing this process. And then so all the stresses and conditions change, and it's more likely that pump A is going to have problems rather than pump B. And that's where I tend to go, you might want to look at other modeling tools than block diagrams at some point.
Well, I mean, again, the block diagram might be 100% right. It's the equations you use to model different parts of it. So,
Yeah.
I mean, that's I think where people get hung up on. The standards aren't particularly helpful, as per usual. They say,
Yeah.
well, if it's this, you use that. Be aware that it might not be, but if it isn't, you can still use this. It's just, all right.
Well, when do you go to, the switching systems or various, I always use the word states. I don't know if that comes from Petri nets or some other style of modeling,
Degraded states, yeah.
but that becomes difficult or more complex in a block diagram than in a system of system modeling that allows you to account for those degraded states or altered states or variables, uh, interactions and all those kinds of things.
And that's where Monte Carlo simulation can be really helpful. I think people shy away from that, but even Excel can give you really accurate numbers if you know how to use Monte Carlo simulation well.
Yeah.
It takes a little time to crank the handle, but we're talking. So even if Excel has to sit there for 2 minutes punching at the numbers for you, that 2 minutes is not a long time in terms of project schedule.
No, it's yeah, and you get way better answers. So but the basic idea, and to summarize this basically, is that there's lots of different ways to approach modeling. And I agree. If you got to start with what you're trying to achieve, what are you working on? What's the purpose? And that kind of puts some guardrails on saying, well, how accurate does this need to be? And if I have a redundant system, do I need to account for and estimate the common cause type failures? And how, and do I need to get the next level of data? Or if I'm accounting for different states and different circumstances, is it suffice? Do I do a fault tree that's, catastrophic loss or loss of production? And it might be a completely different logic structure in that, which is fine. It doesn't need to be all in one model. You pick what you're trying to achieve, what decision you're trying to inform, and then build an appropriate algorithm or system or model or whatever it's called to address that particular issue.
I'd actually go as far as saying if you are actually interested in different failure modes, like safety critical ones or operational ones or logistic one, whatever it is, or failure modes where someone could die or lose a limb. That's one failure mode. Another failure mode is you can't operate at peak throughput. Another failure mode. Another failure mode is you can't even operate at degraded throughput. Another failure mode is you can't operate with any throughput. Technically, if you want to take it seriously, you need to have a separate model for each one, because that emergency relief valve is not necessary for your manufacturing line or whatever it is to keep working. Your line can happily work without that emergency relief valve happening, working, I should say. It's just that when something goes up, you just all might die. So, which is frowned upon these days.
Yeah, it is frowned upon. So anyway, there's always more to it, and it starts with that. I think the key, we should probably rename this to critical thinking, but I'll leave it as it is, because that'll scare people away from listening to the podcast, I guess. And that was based on a couple of questions about, well, how do I go about modeling this? And like I've said many times on the show, is we really do like these kinds of questions or any kind of questions you have on your mind. So if you've got a question about system modeling or about statistics or about dealing with a reliability program of some sort, or I don't know, pick your question, let us know what's on your mind, and head over to ascendoreliability.com/go/SOR. A couple of ways to get in touch. And Chris and I and the other hosts of the show are available through LinkedIn and our About pages. So I try to keep that model of contacting us pretty simple and lots of options for you. So there you go.
Oh, Fred.
Yeah.
Good chat, as always.
As always. Thanks, Chris. Talk to you again soon.
Always a pleasure.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.